There is a question in computer science that a 10-year-old can understand, that has a $1 million prize attached to it, and that some of the cleverest people who have ever lived have failed to answer for more than 50 years. It is not an obscure curiosity. The answer decides whether the encryption protecting your bank account, your messages, and every payment you have ever made is genuinely secure, or merely secure for now. And here is the question. If a computer can check an answer quickly, can it also find that answer quickly? That is it. That is the whole thing. It sounds almost trivially simple, and by the end of this video you will understand why it is one of the deepest open problems in all of mathematics. Some context on how seriously this is taken. In the year 2000, the Clay Mathematics Institute chose 7 unsolved problems that it considered the most important in mathematics, and attached a $1 million prize to each. In the 26 years since, exactly one has been solved. That was the Poincare conjecture, cracked by Grigory Pellman, who then declined the $1 million and declined the Fields Medal as well, and withdrew from mathematics entirely. P versus NP is on that list of 7, and it is the one that computer scientists care about most. Let's build the idea from something you already know. Take a hard Sudoku puzzle. It might take you an hour of genuine effort to fill in. But if I hand you a completed grid and ask you whether it is correct, you do not need an hour. You scan each row, each column, each box, and in about 30 seconds you know. Solving is hard. Checking is easy. And once you notice that gap, you see it everywhere. A jigsaw puzzle takes an afternoon to assemble and a glance to verify. Splitting an enormous number back into the 2 primes that made it is brutally hard, but checking a proposed answer just means multiplying 2 numbers together. Finding the shortest route through 50 cities is hard, but adding up the length of a route I hand you is trivial. And a mathematician might spend a decade finding a proof that a referee can verify in a week. So computer scientists gave these 2 groups names. P is the set of problems a computer can solve quickly. NP is the set of problems where, if somebody hands you a proposed answer, a computer can check it quickly. And I keep saying quickly, which is doing a lot of work in that sentence, so let's pin down exactly what it means. Quickly means polynomial time. If your input has n items, the work your algorithm does grows like n, or n squared, or n cubed, or n to any fixed power. What it must not do is grow like 2 to the n. That is the line. On one side, problems that stay solvable as they get bigger. On the other, problems that fall off a cliff. And this table is why. Look at what happens as the input grows. At 10 items, n squared needs 100 steps and 2 to the n needs about 1,000. Barely a difference. At 50 items, n squared needs 2,500 steps, and 2 to the n needs about 1,000 million. At 100 items, the exponential column has passed 10 to the 30. And at 300 items, 2 to the n exceeds the number of atoms in the observable universe. So please understand, exponential is not a synonym for slow. Slow means you wait. Exponential means you never find out. And here is the part people miss. If your algorithm is exponential, buying a computer 1,000 times faster does not let you handle 1,000 times more data. It lets you handle about 10 more items. That is all. You cannot buy your way out of exponential growth, ever. First question, pause the video. Sorting a list of n numbers takes roughly n log n steps with a good algorithm. So, is sorting in P? And is sorting in NP? Think about both, because the second one trips almost everybody up. Answer in the comments and I will tell you in a moment. Sorting is in P, obviously, because we have fast sorting algorithms. But sorting is also in NP, and that is the bit people get wrong. NP is not the set of hard problems. NP is the set of problems that are easy to check, and anything you can solve quickly you can obviously also check quickly, just by solving it again yourself. So every problem in P is also in NP. P sits entirely inside NP. Which reframes the question properly. We know P sits inside NP. What nobody knows is whether NP is strictly bigger. Is there at least one problem that is easy to check but genuinely, fundamentally hard to solve? Or is every easily checkable problem secretly easy to solve, and we simply have not been clever enough to find the algorithms yet? In 1971, Stephen Cook, and independently Leonid Levin working in the Soviet Union, proved something that reorganized the entire field. They showed that there exist problems inside NP that are, in a precise sense, as hard as every other problem in NP. Not merely difficult. Maximally difficult. If you could solve one of those efficiently, you could solve everything in NP efficiently. These are called the NP-complete problems, and the word complete is doing something specific. It means every other problem in NP can be efficiently translated into this one. They are all, underneath, the same problem wearing different clothes. Which gives us the single most dramatic fact in complexity theory: find a fast algorithm for any one NP-complete problem, just one, and every problem in NP becomes fast. The whole class collapses. A year later, in 1972, Richard Karp published a paper showing that 21 well-known problems that had been studied separately for decades by people who had no idea they were related, were all NP-complete. The traveling salesman problem. Coloring a map so no two neighbors share a color. The knapsack problem. Clique. Vertex cover. Subset sum. 21 different research communities discovered they had all been banging their heads against the same wall from different sides. And these are not Blackboard curiosities. Scheduling exams so no student sits two at once is NP-complete. Packing a lorry efficiently is NP-complete. Planning delivery routes, laying out a microchip, allocating registers inside a compiler, aspects of protein folding. Every one of these is a problem that industry needs solved every single day, and everyone sits in the class where we do not know whether an efficient algorithm exists. Second question. Suppose tomorrow somebody announces a genuinely fast, polynomial time algorithm for graph coloring. What does that immediately tell you about the traveling salesman problem? Pause and think it through, because if you have followed the last 3 slides you already have everything you need. The answer is that it tells you everything. Graph coloring is NP-complete, so anything in NP can be translated into it. A fast algorithm for graph coloring is therefore a fast algorithm for the traveling salesman problem, and for scheduling, and for every other problem in the class. It would mean P equals NP, and the person who announced it would collect the $1 million that afternoon. That is the domino effect, and it is why this one question matters so much. Which brings us to the interesting part. Suppose it is true. Suppose P equals NP and someone finds the algorithm. What actually happens to the world? Start with the bad news, because it is spectacular. Essentially all public key cryptography rests on exactly this gap. Take RSA, multiplying 2 enormous primes together is easy. Taking the product apart again is believed to be hard. That asymmetry is the entire foundation. Factoring is in NP, because checking a proposed factorization just means multiplying. So if P equals NP, factoring moves into P, and RSA stops working. And RSA is not alone. The padlock in your browser, bank transfers, card payments, encrypted messaging, digital signatures that prove a software update really came from its author, every cryptocurrency in existence. All of them rest on the assumption that certain problems are hard to solve and easy to verify. A proof that P equals NP, together with a practical algorithm, would put all of it in question at once. But the same collapse would be, in every other respect, one of the greatest events in human history. Every optimization problem that we currently solve approximately, we would solve perfectly. Drug design. Protein folding. Logistics with genuinely optimal routes rather than good guesses. Power grid balancing. Chip design. Every timetable, every supply chain, every allocation of scarce resources, solved exactly rather than roughly. And then there is the consequence that genuinely unsettles mathematicians. Checking whether a proof is valid is a mechanical process. It is in P. So if P equals NP, then finding a proof of a given length is also easy. Feed in a conjecture, get back a proof, if one exists. Kurt Gödel wrote to John von Neumann about essentially this in 1956, before the field even existed, and he understood immediately what it meant. Mathematical creativity, the thing that feels most irreducibly human, would become a search that a machine performs faster than you. So which way does it go? William Gassarch has polled the research community 3 times. In 2002, about 61% said P does not equal NP. By 2012 it was around 83%. In 2019, about 80% of 124 respondents. And among the specialists who actually work on this problem directly, it is close to unanimous. The overwhelming expert consensus is that P does not equal NP. But notice what that consensus actually rests on. It is not a proof. It is an argument from failure. Thousands of extremely capable people have attacked these problems for over 50 years, with enormous commercial incentive, and nobody has found the algorithm. That is genuinely suggestive. It is also exactly the kind of argument that has been wrong before in mathematics. So why can nobody prove it? And this is my favorite part, because the difficulty is not what you would expect. To prove that P equals NP, you only need to find one algorithm. Hard, but conceptually simple. To prove that P does not equal NP, you have to prove that no algorithm exists. Not that the ones we have tried fail. That every possible algorithm, out of an infinite space of them, including all the ones nobody has thought of yet and never will, must fail. That is a statement about the limits of computation itself. And here is what makes it genuinely humbling. There are 3 famous results in this field that are not attempts at the proof at all. They are proofs that entire families of proof techniques are incapable of settling the question. Every time researchers built a promising toolkit, somebody proved the toolkit could not reach the answer. The first is relativization, from Baker, Gill, and Solovay in 1975. They imagined giving every machine access to a magic oracle that answers one type of question instantly, and they showed something devastating. There is an oracle under which P equals NP, and a different oracle under which it does not. Any proof technique that would still work if you handed the machines an oracle therefore cannot possibly settle the real question, because it would have to prove both answers. And that single observation eliminated the standard technique the field had been relying on. The second is natural proofs, from Razborov and Rudich in 1994, and it is beautifully perverse. They looked at essentially every technique anyone had used to prove that a problem is hard, and found they all shared a common structure. Then they proved that any argument with that structure would, as a side effect, break the pseudo-random generators that modern cryptography depends on. So either your proof technique fails, or it destroys the very hardness assumptions you were trying to establish. The third is algebraization, from Scott Aronson and Avi Wigderson in 2008. Researchers had invented clever algebraic methods specifically to escape the relativization barrier, and those methods produced real results. Aronson and Wigderson then showed that those methods hit a barrier of their own. So the field has now proved, 3 separate times, that the natural way forward is blocked. Which has not stopped people trying. Gerhard Woginger maintained a public list of claimed solutions, more than 100 of them since 1986, and they split roughly evenly between claims in both directions, with a few claiming the problem is unprovable. Not one has survived. The most famous recent attempt came in 2010, when a researcher at HP Labs circulated a claimed proof that P does not equal NP. It got serious attention from serious people, which is rare and to his credit. Within a few weeks the experts had located fundamental problems in the approach, and the consensus today is that it does not work. Third question, and it is a trap, so think carefully. Suppose tomorrow somebody proves that P does not equal NP and collects the $1 million. Does that prove your encryption is safe? Pause the video. The answer is no, and almost every explanation of this topic skips it. NP hardness is a statement about the worst case. It says that some instances of the problem are hard. Cryptography needs something much stronger. It needs the specific instance an attacker faces, generated randomly by your key generator, to be hard essentially every time. Worst case hardness and average case hardness are different claims, and P not equal to NP only gives you the weaker one. So a proof would be a magnificent scientific achievement and would change almost nothing about your practical security. And the reverse holds too. Even if P equals NP, that does not automatically mean the sky falls. The proof might be non-constructive, giving no actual algorithm. Or the algorithm might run in n to the power 100, which is polynomial, and therefore counts as efficient by the definition, and is also completely unusable on any input larger than about 3. The theory and the practice are further apart than the headlines suggest. All right. That is the theory. Let's make it useful, because there is a very practical skill hiding in here. The practical skill is recognizing when you have walked into an NP hard problem, because the symptom is a junior engineer spending 3 weeks trying to write an exact algorithm that cannot exist. The smell is this. You are asked for the best arrangement, ordering, grouping, or assignment. There are constraints that interact with each other. And the number of possible choices multiplies rather than adds. Scheduling, packing, routing, assigning. If your task looks like that, stop and check before you start. And here is what you do instead, and none of it is giving up. 1. Approximate. For many of these problems there are algorithms guaranteed to land within a few percent of optimal, instantly. A route 5% worse than perfect, available now, beats a perfect route available never. 2. Use heuristics. Greedy methods, local search, simulated annealing. 3. And this is the one most programmers do not know, hand it to a solver. 4. Exploit your special case, because real-world inputs are almost never the worst case. 5. Shrink the problem. An exponential algorithm on 20 items is instant. And that leads to the loveliest irony in the whole field. Boolean satisfiability, SAT, is the original NP-complete problem, the one Cook proved it about in 1971. It is the definition of intractable. And yet modern SAT solvers, which are free and which you can install this afternoon, routinely chew through industrial instances with millions of variables, and they are used every day for chip verification, software analysis, and scheduling. The worst case is genuinely hopeless. The cases that actually turn up in the real world, very often, are not. Never confuse a theoretical worst case with the input on your desk. Quick exam corner, because this comes up constantly in tests and interviews and people mix the 3 terms up. NP means checkable quickly. NP hard means at least as hard as everything in NP, and note carefully that an NP hard problem does not have to be in NP itself, it can be far worse, including problems that are not even decidable. NP complete means both at once, in NP, and NP hard. So NP complete is the intersection. Halting is NP hard but not NP complete. Get that distinction right and you are ahead of most candidates. So where does it stand? Open since 1971. The $1 million is still sitting there. The overwhelming majority believe P does not equal NP. Nobody is close. And 3 separate barrier results tell us that the obvious ways forward are blocked, which means the eventual proof, if it ever arrives, will require a genuinely new idea that nobody currently has. And I want to leave you with the version of this problem that I find most beautiful. Strip away the mathematics and P versus NP is asking whether creativity is fundamentally harder than judgment. Whether coming up with the answer is genuinely, irreducibly more difficult than recognizing a good one when you see it. Every one of us assumes it is. It is why we admire the composer more than the critic. And after 50 years, nobody on earth can prove it. So which side are you on? P equals NP, or P does not? Put your answer in the comments and tell me why, because I read them. If this was useful, subscribe. The next deep dive walks through exactly how a real intrusion happens, step by step, from the first piece of public information an attacker collects to the moment data leaves the building, and what stops it at every stage. Thanks for watching.